Hey everyone, welcome to Edureka's video on the most frequent data warehousing interview questions. My name is Bindu Kumar and I'll be helping you with the answers for some of the questions that are asked in most data warehousing interviews. So let me introduce myself. My name is Bindu Kumar and I have been associated with the DW and BI community for the last 12 years. I have worked across multiple domains and organizations of different scale, from a startup to a large MNC giant. Now, in these 12 years, I have worked across multiple tools and the different aspects of data warehousing, all the way from the database and data modeling till reporting and visualization. And when it comes to technology, I worked on the most popular data warehousing tools such as Informatica, Business Objects, Cognos, MicroStrategy, Tableau, and others, to name a few. So let's get started with the popular interview questions and their answers. The first obvious question that's usually expected out of a candidate is, what is a data warehouse? Now, before I answer this question, we first have to understand what is business intelligence, right? Because the words business intelligence and data warehouse are very closely related to each other. Business intelligence is the process by which we collect data about a business, we analyze the data, and then take action. This is the definition of business intelligence. Data warehouse is the technology that supports business intelligence. So data warehouse is the collection of tools and technologies that help a business collect data from multiple processes, organize the data, and enable business intelligence. Many times people often mistake that data warehouse is an appliance. It's a different kind of software. So let me tell you, data warehouse is not a different kind of software. Data warehouse is implemented in the same database as a transactional system. The difference is on how you organize the data and how much data you store in a data warehouse. So usually in a transactional system, you store minimal data, whereas in a data warehouse, you store current plus historical data, right? That being said, a data warehouse or a transactional system can be implemented using the same software, such as Microsoft SQL Server or Oracle or MySQL. So as you can see the definition in this slide, data warehouse is nothing but a relational database designed for analytical needs, and it's a central location where data from multiple data sources are stored, which then can be accessed exclusively for data analysis and visualization by using business intelligence tools such as Tableau or Business Objects. Next question is, what is the basic difference between a data warehouse and an operational database? Or in other words, what is the difference between a data warehouse and a transactional system? So think about the dashboard of your car. There are some metrics that are shown to you, such as a speedometer. The speedometer shows you what is the current speed that you're doing right now, right? What happens if the speedometer stops working? It's a real hazard because you could be operating the vehicle beyond its permittable limit, right? Or you could be breaking the speed limit in that territory. So the speedometer is an example of an operational system or a transactional system. Why? Because it helps you run the business. So transactional systems help you run the business. On the other hand, a data warehouse helps you analyze the business. In the dashboard of a car, an odometer is an example of a data warehouse because it's not showing you current information, but it's showing you historical information. What is the total miles that you have put on your vehicle, right? And if the odometer were to stop working, it won't cause any hazard. You can still live without it for a couple of days. This is the fundamental difference between a data warehouse and a transactional system, which is a transactional system is very much necessary for ensuring your business runs all the time, whereas a data warehouse is necessary for not running the business, but for analyzing the business. How well is the business performing? And given these needs, a data warehouse contains historical information, which helps in analyzing business metrics over time. And the most frequent operations that happen in a data warehouse is the reading of the data, right? So data is written once, but the read happens many times over. And the end users are usually business analyst and data analyst. On a transactional system, you maintain as minimum data as possible. That is because you want to ensure that your application keeps running as much as with high performance as possible, right? And in a transactional system, there are large number of transactions that happen, which include create, insert, updates, and deletes. And the end users of transactional systems are users who are necessary for running the business, such as operational team members. All right, we have a question from Vardhan. Vardhan is asking, is a data warehouse OLAP and is a transactional system OLTP? Absolutely, right? So OLAP, or in other words, online analytical processing, is a class of applications that help you analyze information. And data warehouse clearly belongs to a OLAP category, whereas a transactional system belongs to OLTP category. So OLTP stands for online transaction processing. The next question is, what is data warehousing? As I already explained in the first slide, data warehousing and business intelligence are related. Data warehouse is the technology piece that helps you collect data from multiple sources of the business and keep it in a centralized location from where it can be accessed for reporting. So if you look at this diagram, it shows you a typical architecture of a data warehouse. So looking at the diagram from the leftmost side, you have the data sources. So data source can be a database, or it can be a unstructured system such as flat files or CSV files. All of this data initially is kept in a common database, which is called a staging area. Now the staging area is considered a part of your data warehouse. So once the data is stored in a common location, it makes it much easier to integrate the data and clean the data and then move the data forward. As we move the data forward, we transform the data from the staging into dimensions and facts and other supporting data types such as aggregate data and metadata. We will look at what is metadata and aggregate in few slides later. Once you have the dimensions and facts, from here we move the data to data marts. Now this is an optional layer. The data marts can be physical databases, or they can be simply logical grouping of these data. So for someone who's accessing the sales data mart, they will only get to see the dimensions and facts which are relevant for sales. The same applies for purchase and stock. And when it comes to the user group can access the data mart or the data warehouse either directly using a database query editor, or they could be accessing the data through a reporting tool. Next question is, what is OLAP? So OLAP can refer to a class of applications. At the same time, it can refer to a specific set of tools as well. So let me give an answer for both. OLAP stands for Online Analytical Processing. So if you were to divide all the computer applications into two major classification, one would be OLTP, the other would be OLAP. The OLTP, or the Online Transaction Processing, are the systems where the data originates. An example of that would be a point of sale in a retail supermarket. So that is where you bill your products and an invoice is generated, right? And an event has occurred and the data has been generated, which is stored in a database. So that's an example of an online transaction processing. Online analytical processing, on the other hand, does not originate data, does not create data. Instead, it is used to analyze existing data, right? An example of OLAP is your data warehouse, right? So data warehouse is built to collect data from other OLTP applications and then analyze them. So this is a broad understanding of what is OLAP system. Now, talking specifically about BI tools, OLAP refers to a certain set of tools that load the data directly in memory. And an example of that is SQL Server Analysis Services from Microsoft, or SSAS for short. So what exactly is OLAP? In other words, it's also called as a OLAP cube. So if you look at the tables in your data warehouse, they are not very different from any other tables. It's just that we follow a convention called as dimensions and facts. At the end of the day, you still have to join these tables using primary key foreign key relationships to analyze the data. OLAP cube, on the other hand, takes all of this data together, does the join, gets the aggregate data and stores it in memory. And the data is stored in a proprietary format. Once it is stored in memory, anybody can access the data in the cube by simply using a spreadsheet like application, including the Excel spreadsheet itself, you can connect to a cube and you can simply drag and drop attributes to get the data. Since the data is already joined and pre-aggregated and it's in memory, the data retrieval is quite instantaneous. One does not have to write any SQL query to get the data. So talking specifically about a tool, when we say OLAP, we are referring to OLAP cubes. Okay, Prakash has a question. Is Tableau a OLAP tool? So, all right, Tableau can do both. Tableau can act as OLAP tool. It can also connect to a database. So there is an option of live and extract in Tableau. When you set it to extract, Tableau will get all the data and it can either keep it on the Tableau server or you can cache it in memory. So anytime anybody refreshes the report, the data is going to be returned from the memory or the server cache instead of the database. So yes, Tableau can act as a cube when configured the right way. Moving on. Another question that's most frequently asked is, what is OLTP? How is OLAP different from OLTP? So just a few slides before, we discussed the example of a car's dashboard, right? So expanding on that example, any system that is absolutely critical for running your business can be thought of as OLTP. Any system that is used for analyzing how your business is running can be considered OLAP. And when you start this classification, you'll realize that OLTP systems are quite critical for the business. Any downtime is not tolerated, whereas OLAP, on the other hand, are not business critical. Even if there is a downtime of few hours to few days, it can still be tolerated. However, they are quite important for analyzing your business. An example for this would be a point of sale. Point of sale in a retail super chain is an example of OLTP where if there is a downtime, if you cannot check out your products, if no bill can be generated, then the business comes to a halt, right? So think about an OLAP. So there is a area sales manager who is responsible for looking at the sales metrics. Now for the sales manager can look at the sales metrics on a daily basis or a weekly basis. However, if the metrics were not to be available for a single day, it won't stop the business, right? So that's an example of a OLAP. Given these differences between OLTP and OLAP, the way the data is organized and the amount of data that is stored between OLTP and OLAP is very different. Okay, Meena has a question. Is banking system an OLTP or OLAP? Good question, Meena. So let me explain the OLTP and OLAP components within a banking system. Now, I'm sure all of you have a bank account and you must have a bank application installed on your smartphone, or you probably go to the website, right? So what you'll notice is that when you log into the bank application, there is a place from where you can look at all your historical statements, right? So usually there is a link and it will let you select the past 60 days or the past 90 days set of transactions, right? And anything beyond 90 days is not available. If you still want transactions older than that, there would be a separate link which would say something like download historical statement. That would be a separate link. So these two links are there for a reason, right? So the reason that there is not a single link is because banks generate a whole lot of information, right? Every customer contributes to a large number of transactions on a daily basis. If all of it were to be stored in one application, which is in the bank application, the performance would be severely degraded. So what banks do is they store the minimal amount of data in the OLTP system. The rest of the data is stored in the OLAP system, and which is why you have two different links. Moving on. What is a dimension table? This again is quite an obvious question, and especially if you're new, you're often wondering what exactly is a dimension table. Dimensions and facts are at the heart of a data model in a data warehouse. So let me put it this way. Assume that you are the area sales manager and you are interested in how the sales organization is doing. So if somebody mentions to you that, yes, today we sold 10,000 units of several products, just the number 10,000 doesn't add any value. You really cannot understand whether you're doing good, whether you're doing bad, what is the room for improvement. That is where we need some context. We need ways by which this number 10,000 can be divided. So you will naturally ask questions such as, if today's sale is 10,000, how much was the sale yesterday? What are my top 5 products? What are my top 3 stores? Who are my top 5 customers? And so on. So the entities by which you divide the data become your dimensions, and the measurement itself becomes a fact. So dimensions are entities that give context to the data. So for example, in a retail chain, if sales is a fact, if sales is a measurement, then the dimensions for that would be product, customer, date and time, store. So these dimensions give a whole new meaning by which you can slice and dice the data. So the earlier $10,000 can now be divided into $5,000 per store, or we sold $7,000 within first half of the day and $3,000 towards the end of the day, and so on. That gives context using which you can take further action. In other words, dimensions answer the 7 questions of a business event. And those 7 questions are who, what, when, where, why, how, and how many. So any business event such as sales or a banking transaction can be associated with 7 of these dimensions. So let me repeat that again. Who, what, when, where, why, how, and how many. Each dimension usually has a set of attributes. For example, if there is a customer dimension, the attributes for a customer dimension would be customer first name, middle name, last name, age, date of birth, contact number, address, and so on. These are called attributes. And all of the data related together, since they are related to a customer, they are collectively called as a customer dimension. What is a fact table? So as I explained in the previous slide, dimensions or facts are at the heart of the data warehousing data models, right? So a fact is the business event. Fact represents the grain of the business event that is to be measured. So for example, if sales is a business event, the fact would be how many number of units did we sell? What is the total selling amount? What did it cost us to buy? What is the discount amount? What is the tax amount? And so on. All these are called facts. The difference between a fact and a dimension is that dimensions can be independent, whereas facts are not. So let me explain that with an example. When you walk into a store as a customer and you purchase a product and you finally get them billed, right? A transaction is created. And that moment when the bill is generated, there are a couple of things that happen. You as a customer walked into a store and picked a couple of products. Before this event happened, all of these dimensions existed already. It's just that they were not related to one another. So you as a customer were already there, the store was already there, and so was the product. It's only because of the sale that all of these dimensions are related together now. So the business event that brings together the dimensions into a transaction is usually what becomes a fact table. So a fact table is dependent on the dimensions. And there's one other interesting thing that happens. When a business event occurs and it is captured into a fact table, it not only captures the different dimensions that are related with each other, but also it gives rise to some numbers. An example of that would be tax amount, discount amount, and the total selling amount. These were numbers that did not exist anywhere before, but were generated as part of the transaction. These numbers are called measures. So as you can see here, a fact table contains two kinds of data mostly. A dimension key that can be tied as a foreign key relationship to any of the dimensions, and a measure. So a dimension key here can be a customer ID or a product ID, and a measure can be total number of products sold, or what is the total selling amount, and what is the tax amount, and so on. Moving on, what is the level of granularity of a fact table? Now this is quite an important question. So what exactly is grain? Now these questions can come to you in different ways. So For example, the interview will ask, what is the grain of a fact table, or how do you decide the grain of a fact table, and why is it so important? So the grain is nothing but the level at which the business event occurs. Okay, so let me give you an example. Now, if a sales manager wanted to record the sales of a store, she can do it at a level of a day, meaning you simply consolidate all the sales that happened in a day and you just show one number that shows, okay, today's sales were $5,000, yesterday's sales was $3,000, and so on. So that grain is at a day level. Although it seems to serve the purpose, there are many questions that cannot be asked, such as what are my top selling products? Who are my top 3 customers for today? And so on. That is where we need to lower the grain a little bit more. So we need to capture the individual transactions that happen. And when we start doing it, the fact table will have one record for every transaction that is made. So let's assume that every customer who makes a purchase has a sales order ID generated. Now, if you think the sales order ID is the grain of the fact table, you could be mistaken. Because if you look at a sales order ID, it's quite possible that a customer can purchase multiple products and multiple units of every product. So given this, the sales order ID is not the grain. The real grain is a combination of sales order ID and a product. So let's see if this can be broken down even further, right? So a customer walks in to a store, he purchases 2 products, right, and generates a bill. There is nothing more atomic than that. So that is the lowest grain of the fact table for a sales. So I repeat, the grain of a sales table will be the sales order ID and the individual product ID. So for each sales order ID, there could be multiple records in the fact table. Now getting this grain is very important because if you get the grain right, then it involves a lot of dimensions, which in turn makes your data model very rich in terms of what are the kind of questions you can ask. Going back to the example I started with, which is the sales manager just wants the daily sales. If that was the case, the only dimension that can be attached to that model is the time dimension. All right. So you're just saying, what was my sale yesterday? What is my sale today? And so on. By lowering the grain to the naturally occurring grain of the business event, which is a sales order ID and a product ID, we can now ask very rich questions to the data model, such as show me my top 3 customers for today, show me the top 5 selling products for today, show me the discounts or the promotions that were used today, and so on. Okay, Madhav has a question. Can the grain of a fact table change? Good question, Madhav. So if the business users who are the stakeholders in the data warehouse and the data modelers who are responsible for creating the dimension facts, if they have done a proper groundwork and a prototype at the very initial level of designing a data warehouse, then they should have got the grain right the first time itself. If not, due to some reasons, if the grain was not correct, then there are chances of correcting it later. However, the impact can be severe, especially on any reports that you may have created. So in cases when the grain of the fact table is changing, it's always advisable to create a new fact table with the new grain and slowly move all the reports and dashboards from the older fact table to the new fact table. So that way your reports do not break immediately and you do not disturb the existing fact table. Right. Moving on. What is the difference between additive, semi-additive, and non-additive facts? This again is a popular question, and sometimes there seems to be some confusion, right? So if you look at the definition here, an additive fact is a measure that can be fully summed across any of the dimensions. So what that means is, if you look at the selling amount or the sold amount that is there in a sales fact table, it can be rolled up across any of the dimensions. So for example, you can write a query such as, show me the total sales amount per day, or show me the total sales amount per customer, or by store, and so on. So the sales amount or the sold amount is a number or a measure that can be aggregated across any of these dimensions. So which makes it a additive fact. And of course, the aggregation that we would be applying would be a summation on the sold amount. A semi-additive fact is a measure that can be summed across only some dimensions, but not all. An example of that would be the daily average balance of a bank account holder. This number can be summed up across customer dimension, but not really a time dimension. And let me tell you why. So let's say my daily average balance for yesterday was $50 and my daily average balance for today is $60. So if I were to do a summation of it over time, it would mean for 2 days, my daily average balance was 50 plus 60, which is $110, which is not right. So you would have to do an average of it, right? So if you were to do the same summation across a different dimension, such as customer, it would make sense. So for example, show me the total daily average balance across 100 customers. So it would maybe show a number like $1,000, which is still fine, right? It makes sense. So the daily average balance in a banking fact table is an example of a semi-additive fact. And sometimes, the questions that are asked is, how do you restrict a semi-additive fact? Because we say here, it cannot be summed up across other dimensions. So is there something that restricts? The answer is no. There is nothing that restricts. You can still roll it up across all the dimensions and you will get a number. The question is, does it make sense, right? So in the example that I gave, I can write a query which will show me $110 when rolled up by a time dimension, but that number does not make sense. So the difference between additive and semi-additive fact is that there's nothing that's going to stop you from generating these numbers or aggregating these numbers in a query. It's just that for us to decide, does that number make sense? Can it be rolled up across a dimension? And finally, non-additive fact. So an example of a non-additive fact is any ratio or a percentage or any calculated measure that is pre-calculated and stored in the fact table. An example in a sales fact table would be a discount percentage. So since it's a percentage, it's already aggregated. If you were to sum it up by time or by customer or any other dimension, it really may not make sense. So for example, if I were to say, do a sum of all the discounts that we did today, and it would show up a number like 5,000%, which really doesn't make sense. The next question is, what is a factless fact table, right? Again, this is quite a popular question and there seems to be some confusion about it. So a factless fact table is a fact table as we discussed before, except that it only has connections to the dimensions but no measure associated with it. So think about a charity organization, right? Just imagine you do not make a sale in a day, you just simply give out products for free to your customers. So what happens? Your customers walk in, they pick the products that they want, they don't generate a bill, they just walk out. They probably just enter a form saying, okay, I've picked these products. When that happens, you don't have a sold amount, you don't have a tax amount, discount amount, you don't even have a number of products. You just know that the customer walked in into this store in this date and time, right? And they went away with these many products. So when you have a business event like that, that is called a factless fact table, right? Because that fact table simply captures the interaction between the different dimensions without any facts to it or without any measures to it, such as sold amount. So the example that I gave for the retail chain, may not happen in reality, but another example that I could give you is, let's suppose there is a seminar and you are collecting statistics of the people who are visiting, right? So people who are attending the seminar. So you would capture things like what is their age group, what is their gender, which area or state they are coming from, right? And maybe other details. So your fact table will have a link to all these different dimensions, such as date and time, what was the topic of the seminar, and so on. But if you look at the fact table itself, the fact table will simply have dimension keys without any measures because there simply is no measure for this business event. Moving on. What are conformed dimensions and conformed facts? In layman's language, conformed dimensions is nothing but a reusable dimension. So dimensions once created for a department can be used across multiple departments. So if you were to follow Ralph Kimball methodology of building a data warehouse, you will realize that when you start building a data warehouse for an organization, you usually start with the department that needs it most. So let's take an example of a startup firm which is into a retail industry. So in retail, your first and foremost focus is on sales. You want to increase the sales. So obviously you would want to build a data warehouse for sale. And when you do that, you create multiple dimensions. You define new dimension tables. So in a retail, you would have dimensions for customer, product, address, store, date and time, and so on. Now let's assume the data warehouse is built and the sales department is using it. And after a while, you want to build a data warehouse for, let's say, the shipping department. And when you begin with that, you realize that some of the dimensions that are required for shipping are already built in sales, such as customer and product and date and time and even the address. Because you are shipping to a customer, you're shipping a product to a customer on a date and time for a specific address. Given all these common data points between the sales and the shipping department, you simply reuse the existing dimensions. So that is an example of a conformed dimension, where dimension once built for a department can be used consistently across other departments in the same organization. Similarly, we also have the concept of a conformed fact. So conformed fact could be business events that are of interest for multiple departments. So for example, when a sales order is placed, it's not only the sales department that's interested in it, but even the shipping department and maybe the inventory department as well, because they want to prepare for their workflow. So in which case, we share those fact tables or measures across the departments. So that's an example of a conformed fact. And related to a fact table is an aggregate table. So let's look at a retail chain as an example again. In a retail scenario, there could be millions or even billions of transactions on a daily basis. And for someone who's responsible for analyzing the sales, it would be a very tedious effort to look at all the millions and billions of sales as individual records. Instead, they probably want to look at the aggregate. They want to condense the information. So all they're looking is, what is my daily sales, right? What is the profit for today? How many number of units did we sell today? In such case, we do an aggregate over the base fact table and we give them the data. So for someone who's looking at just the sales by hour, we would probably give them a report containing 24 records or 24 rows in a simple table, with each row showing the count of the number of units sold per hour. So this is fine, and you can get this data from your base table. However, if this is a common data access pattern, if you have to do it on a regular basis, then it makes sense to get the data out and store it in a separate table. So if your base fact table has millions of transactions for a day, your aggregate table will probably have one record if it's at a daily level, or 24 records if it's an hourly level. So any knowledge worker or a data analyst who's simply looking at the aggregate number can direct their query towards a very small aggregate table instead of the very large base table. This tremendously improves the query performance of a data warehouse. What is summary information? So summary information and aggregate tables are related to each other. So summary information is the place where we store all the aggregate tables. Now this can happen at various levels. We can either persist these as physical tables, or we can keep them in the reporting layer, such as Tableau and business objects. And within these reporting tools, they have cache at multiple levels, such as report level cache, data access level cache, and so on. So wherever the aggregations are kept, that area or that layer is referred to as summary information. Okay. What is ETL? ETL stands for extract, transform, and load. Now, ETL belongs to a broad classification of tools called as data integration tools. Data integration tools refers to a set of tools that are used in moving data from one application to another application. So Informatica, Talend, Unity, Web Methods, these are all examples of data integration tools. Within data integration, we have three more categories, such as ETL, application to application integration, as well as replication, of which the classification that's of interest here is the ETL. So Talend, Informatica, SSIS, these are examples of ETL. So what is ETL? ETL stands for extract, transform, load. This name has been derived by the architecture of a typical data warehouse, where we usually extract the data from the data sources, we store it in a staging layer, we perform some kind of cleansing and transformation over the data. Now, this transformation can include converting the data into dimensions and facts. And finally, the prepared data is loaded to a data warehouse. Given this pattern of data movement, which is very specific to a data warehouse where we read the data, transform it, and then load it, any tool that is purpose built for this is referred to as an ETL tool. But please be aware that not all tools are ETL tools. So as an example, web methods, Microsoft BizTalk, Actunity, although these can move data as well, they do not have the same features and capabilities of a ETL tool. They are application to application integration or sometimes replication tools. Here are some of the tools that are quite popular in the ETL space. So at the top of the chart is the Informatica, which is very popular across enterprises, followed closely by Talend Studio. So Talend Studio is an open source software which has an enterprise version as well as a community version, and it's quite popular with small startups, mostly because it is completely Java based and it generates Java code as an output. There are other popular tools such as DataStage, Oracle Warehouse Builder, Ab Initio. Then we have SAP Data Services, SSIS, which is from the Microsoft and part of the MSBI stack. And we also have SAS Data Management. Of these tools, I would highly recommend you to pick up Talend and SSIS. The reason is SSIS is quite developer friendly. So if you are from a Microsoft background, it really helps you understand ETL and how it works. And you can give a try for Talend Studio once you're comfortable with SSIS, because Talend Studio has a lot of rich features. Since it's community driven, you will find a lot of plugins and components that you can use to move data from anywhere to anywhere. So for example, Talend Studio can connect to Google Sheets or your Google Drive. It can read data from there and it can publish to a Hadoop file system. I would personally recommend that you pick up at least two of these ETL tools, so that way you get a clear grasp of how these ETL tools work. And you'll realize that most of them have a quite common architecture and how they're implemented. All right, so the next question is, what is a data mart? Now, a data mart, just this definition is often a cause for confusion in many organizations, right? So let me talk about a data mart and a data warehouse. A data mart refers to a data warehouse that is purpose-built for a small department or a single department. A data warehouse, on the other hand, refers to a set of dimensions and fact tables that have been built for the entire organization. A data mart is specific to a department, or it can be specific to a line of business, whereas a data warehouse is built to serve all the departments. And this is often related to the discussion between a Kimball methodology versus Inmon methodology. Rolf Kimball preaches the bottom-up approach of building a data mart for one department at a time and eventually merging all of them into a larger data warehouse. Whereas Inmon suggests that we should build a data warehouse for the entire organization that would serve the needs for all the departments, right? So taking that into consideration, data mart is a small version of the data warehouse, or it is a subset of the data warehouse which deals with a single subject. In other words, deals with a single subject area or department or a business vertical, or in other words, a line of business. Given the scope of a data mart, the time taken to build a data mart is very less compared to build a complete data warehouse for the entire organization. But this is not always true. So if you were to consider a very small startup, it's quite possible that they can build a warehouse for all their departments at the beginning itself. But this really may not work for a very large organization. And for those of you who are attending an interview, you must look out for this question, because in different organizations, they call it by different names. So they may have a data warehouse that is serving multiple departments, yet they refer to it as a data mart, right? At the same time, in other organizations, they may have a very small data warehouse for a specific department, right? And instead of calling it a data mart, they refer to it as a data warehouse. So always make sure that when you get a question like this, you make yourself clear that as per you, this is the definition, which is a data mart is for a specific department or a subject area, whereas a data warehouse is across departments. Okay. Next question, what is metadata? All right. So metadata is defined as data about data. I believe most of you are familiar with that explanation. But what is metadata in the context of a data warehouse? Why is it important? So metadata is often overlooked but quite powerful when it comes to understanding and maintaining your data warehouse. So if the data warehouse is collecting all the data about a business, the metadata itself collects information on what is the source system from which you're collecting the data, what are the table names, what are the data types, and so on. Once this data is collected, it's easy to build a data lineage. It is easy to understand impact. So for example, if a source system is changing, using the metadata, you can identify a certain table and column in the source system. How is it mapped to a corresponding dimension or a fact table in your data warehouse? It shows you the mapping on how the data is flowing. With this information, you can prepare for your changes. Without metadata, even if somebody tells you that, okay, there is a change that's happening in the source system, you will not be able to react in time. You cannot do impact analysis as easily as you can do when you have metadata with. So metadata is often neglected because it is thought of that it's probably not required, but metadata should be created and maintained from day one of building a data warehouse, and it should be continuously updated. Okay, Sheetal has a question. Are there any tools to generate metadata automatically? Okay, that's a good question. So metadata cannot be generated. It can be as long as you're using the same family of tools. So for example, Informatica can generate metadata about the jobs. But what about the reports that are using your dimension tables? What about some other tool like Talend if it is also being used in your project to move the data? How do you maintain the metadata there? So although some of these tools like Informatica can generate metadata, it is specific to the packages that you build using that tool itself, but it cannot support anything outside of it. So I have worked on projects where I have maintained metadata irrespective of the tools. And the idea is to build metadata from day one and continuously update it, keep it away from any automation so that even if the tool were to change, even if the technology were to change, metadata still remains something that can be easily modified. Okay, Pawan has a question. Do users access metadata? Okay, that is quite possible. However, in most cases, metadata is reserved only for the data warehouse developers. So as a member of the data warehousing team, you want to understand how is the data flowing? What are the mapping? What happens if a column in the source table is deleted? All right. So it's of most importance to the data warehouse developer than the business user. However, in some cases, the business user may also want to access this. And those are the kind of users who are very comfortable with the systems, right? And they want to understand where the data is flowing from. What is the source system and what is the corresponding dimension and fact table. So for such power users, yes, you may need to give access to the metadata. Okay. Another question is, what is data mining? How is it different from data warehousing? So before I answer that question, let me give a little refresh about the dimensions and facts. So as we discussed, dimensions are something that give context to the data, right? If sales is the business event, then you have dimensions such as customers, products, date and time, store, geography, and so on. So you can aggregate the data, you can look at the sales by these different perspectives or different dimensions. Data mining, on the other hand, can negotiate across or navigate across all these different dimensions and find hidden patterns. An example of that is when you use your Amazon app or any shopping app. If you're looking at a product and let's say you already bought the product, at the bottom of the screen, you will see some recommendations such as people who bought this phone also bought this case. People who bought this sports equipment also bought probably running shoes and so on. So how is this data generated? So all the transactions that ever happen are stored in a data warehouse, and there are complex data mining algorithms that keep scanning the data. And what they do is they look at the product that you are looking at in real time. They look at the historical transactions, all the sales that have been done by other customers, and they see if there's anything that's common. Is there or was there another customer who bought the same product? If so, what were the other products that the customer bought? And given this information, it would display it immediately to you in the application. This is an example of a data mining. So data mining is slightly different from dimensions and facts in the way that it scans through all those tables and it tries to find correlation between data. But the good thing is data mining is achievable through data warehousing. So what is a data warehouse? Data warehouse is a place where we organize all historical data, right, for analysis. So using that same infrastructure, you can run your data mining algorithms. Okay, Prakash has a question. So I said the data warehouse is historical data, but I'm also saying that the Amazon app is in real time. Very good question. So when I say historical data, what does it mean? Every sale that you ever make, right? All of that goes into the data warehouse. Or let me give you a different example. So let's take a banking application as an example, right? So you can go in and update your contact details or your address details. And when you do, once you have saved the changes, the next time you log in, you will see those changes reflect the new details that you mentioned, right? As far as you're concerned, the data that was earlier there, the contact details, they are gone, right? They have been deleted. But the truth is, they still exist, not in the transactional system, but in the data warehouse. So the data warehouse will keep a track of the number of times you have changed your contact details. And this is how sometimes the banks alert you on some irregular activities, right? So if it feels that you have used two different ATMs at the same time, right? And if they are geographically set apart, then it is historical information processing that helps the bank give you an alert saying, okay, there is some irregularity in your transactions, right? So take that same example. The data mining algorithm is looking at your current activity, which is you're looking at a product, and then it is going to the data warehouse and it works really fast. It works really, really fast. It's scanning all the historical data. So when I say historical data, sales that have already happened, and then it gives you suggestions, right? The Amazon app is an example where there is a blend of real-time and historical data. All right. So what you're looking at right now is real time. You're looking at a product that's there in the inventory. Plus the recommendations that you're looking at are real time as well. However, they are based on historical data. So data mining is very suitable because the way the data is organized in a data warehouse is perfect for running data mining algorithms. Okay. The other popular question that is asked mostly of report developers is what is OLAP servers or what is OLAP cubes? Now these questions can come to you in several ways. What are the different kind of cubes? How do you refresh a OLAP cube? What are the different kind of OLAP architecture and so on, right? So as we explained at the beginning of this slide, an OLAP cube refers to a data structure where the data is stored in memory, right? And users do not have to write a query. The data can be accessed simply by dragging and dropping attributes, right? So there are several architecture styles when building a cube. So let's look at these. The first is a MOLAP or multi-dimensional OLAP. So in multi-dimensional OLAP, you define a cube, which is a set of dimensions and facts. You process the cube. By processing, I'm referring to the fact that you get all the data and populate into the cube, and then you publish the cube into the server or the server's memory. And from there, the users can directly access the data. This has several advantages. One, there is no query being written. Second, the data is retrieved once from the database and stored within memory, which means the performance is going to be very high. The data can be retrieved instantaneously without the user having to worry about where is the data coming from, what are the joins, how many tables are involved, and so on. Some of the shortcomings of multidimensional OLAP is that you can only store a minimal amount of data. The reason is memory or random access memory still is hardware that is not easily procured. It is not cost effective in comparison to, let's say, hard disk or storage. So given this fact, you need to strike a balance between how much data you want to store in the multidimensional OLAP. The next category is relational OLAP. Relational OLAP is very similar to multidimensional OLAP, but here only the cube is published to the memory, but without any data. The data, in fact, is still stored in a database. And the database can be a relational database like SQL Server or MySQL. So what happens when a user accesses a rollup cube? So when somebody accesses this kind of a cube, since the cube does not have any data by itself, it only has the data structure, the cube connects to the database, gets all the data that is required, and then shows it to the user. So the cube does not store any data. It still goes to the database and it can write its own queries to get the data. So this approach has to be taken when there is a severe shortage of RAM, or if there is simply too much data to be stored in the memory. The last category is hybrid OLAP. So hybrid, as the name suggests, is something that has the best of both. And in a hybrid OLAP architecture, you can control what is the amount of data that's stored in the cube or in memory, and what is the data that is stored in the relational database. So you can take a decision based on data access patterns. If there are some tables or if there are some aggregations that are most often used, you can store them in memory, and the data that is used less often can be stored in the database. So this tries to strike a very good balance between the amount of RAM that's available versus how much data you store on the disk. The best example that I have come across so far that implements all these three is again SSAS, which is SQL Server Analysis Services. So when you build a cube in SQL Server Analysis Services, you can control these options per cube. You can precisely say, should it be a molap or rollup or holap? And within holap, you can set the latency. How often should the data be refreshed and so on. I would highly recommend everyone to try out SSAS. So the next question is, which one is faster, multidimensional OLAP or rollup? So if you understand the architecture very well, then the answer is obvious. Since multidimensional OLAP is directly stored in memory and all the data is pre-processed, it is definitely faster than a relational OLAP. Okay, so this again is a trick question. This question can be asked several ways. What are the operations that can be performed by an OLAP cube? There are many operations that can be performed, but the most popular ones are these: roll up, drill down, slice, dice, and a pivot. For some of you already may be familiar with a slice and dice, right? So I'll show you with an example of what exactly that means. The first is a roll up. Roll up a couple of years ago was being referred as drill up. So drill up, drill down was commonly used terms, but then people realized that you can do a drill down into data but not a drill up. Hence, there was a change in how we call drill up. We started calling it as a roll up. So roll up is an operation by which you condense the data, right? You condense the data from many different records to fewer records. Okay, so if you look at this example, you will see that the cube at the bottom of this picture has data organized by two different dimensions. One is the time dimension represented by these quarters, and the other is the city. So if you were to do a roll up and condense the city into country, what you end up is with two records instead of four records, right? So the number of records that is being displayed has reduced in the cube, and at the same time, the metrics have been added up. They have been summed up. So this is a simple roll-up operation, right? And we also use the term dimension reduction. Okay, so these kind of operations are pretty easy in a cube since there is no query involved and all of the data is stored in memory. A roll-up operation can be done instantaneously in a cube. The next is a drill down, which is the opposite of a roll up. So if you see here in this slide, we start, okay, I believe there is a slight issue with the slide. So let me go back to the slide. So a drill down would be doing the reverse, meaning you start with a country, right? And you drill down into the city. So let's say if you're presented with the total sales for today, right? You would want to drill down to see what are my top 5 products and so on. And if you look at the slide, you'll see that the drill down has occurred on the quarter, right? So the quarter is now expanded into the 12 months in a year, right? So you can see the numbers being spread across these 12 months. So this is an example of a drill down. The next is slice, right? And you'll most often hear people talking about slice and dice, especially those who are from a reporting background or data analyst. Let me tell you, slice and dice is just a buzzword. Simply put, slice and dice is an operation of applying filters on the data, right? So let me show that with an example. So if you see here, if you look at the cube at the top, right? Again, we have the data spread across time and the city. Now, if I were to apply a filter on the Q1 slice, right? On the Q1 dimension, just the quarter one, we end up with this small slice as shown in the figure below. So this is an example of a slice. Now a dice takes it one step further. In a dice, we apply a filter by another dimension, right? So here the filters have been applied both at a city level and a quarter level. So we started with the cube that's at the bottom of this picture. We filter on the time dimension by quarter one and quarter two. We also apply a filter on the cities for only Vancouver and Toronto, right? And the end result is a smaller cube. So this is called a slice and dice. So like I said, it's a simple operation of applying filters. Now, the same can be done by writing queries as well. But when you're using a OLAP cube, since you visualize as a cube, you use the word slice and dice instead of saying filters. That's the only difference between slice and dice and a reporting filter. It's just that slice and dice is implemented in a cube, whereas filters or criteria is applied in a query. Next is a pivot operation. Now, a pivot is called by different names. For those of you who are familiar with a spreadsheet, you will know what a pivot is, right? For others who are coming from a pure reporting background, you can think of it as a matrix table that you create in, let's say, business objects, right? So simply put, a pivot table is a data representation across multiple dimensions, right? So you see here, the data is already in a pivot. So on one axis, we have the city, and on the x-axis, we have the phone security types. Now you can switch this, right? You can switch this so that the mobile phone types or the item types in the y-axis and the cities appear in the x-axis, right? So this is called a pivot operation where you change the axis by which the data is presented. Okay, Meena has a question. Where do we use a pivot operation? Very good question indeed. So you use this mostly to save the real estate area on a dashboard. All right. So let's assume you're showing this information as a flattened table. All right. If you're showing the city and the item types as a rows, if you were to display it as flattened rows, then it will occupy close to 8 records in the grid. But if you were to create it as a pivot table, instead of increasing the length of the grid, you are using the width of the grid as well. So that way you save or you make good use of the width of your screen, right? So that's the number one reason of using a pivot table in showing the data. This is a follow-up question on how many dimensions are usually present in a slice and a dice operation. So as I mentioned already, in a slice operation, it's usually one dimension, but in a dice, it is two or more dimensions, right? So the filters are applied across two or more dimensions to arrive at a dice. And the word dice is, refers to the object that we use when we're playing games, because when you apply a filter across multiple dimensions, that's what a cube looks like. Okay. Another question that's asked is, what is data normalization? What is the benefit of data normalization? So let me tell you this. For a data warehouse, you don't do normalization. We follow the opposite, which is denormalization. But yet, why do we ask it, right? Why should we be concerned about it? The reason is people who are coming from a OLTP background tend to do the mistake of introducing the concepts of OLTP into OLAP, right? Of a transactional system into a data warehouse. So as a data warehouse developer, you need to not only know the patterns, but you need to know the anti-patterns as well, right? What are the things to avoid, right? So one such thing is the normalization. So normalization is this process of splitting up the data into as atomic number of tables as possible, right? And there are several forms of normalization. First normal form, second normal form, and third normal form. There are plenty of resources over the internet which will tell you how exactly these work. But the end goal is that you avoid data redundancy And why do we avoid data redundancy? We avoid it so that when there are changes to be made, the changes happen to the one table at a time or one row at a time. So an example would be your banking application again. Let's suppose all of the data is stored as one flat table, right? Your address, your contact details, your name, your email address, your transactions, your preferences, everything is stored as one flat table. If there's a change to even one of those attributes, all of the records that have that value will have to be updated. Now, this is a very costly operation for a database. And remember, banking is a critical application which could be used by multiple users simultaneously. So you want to handle the change very quickly and in a very small place as possible, right? In a single table as possible and in a single row as possible. So given this need, you split the data into very atomic values, and you do that by following the process of normal forms. So this method really helps in improving the performance of a OLTP system or a transactional system, but it works against the favor of a data warehouse. Why? Because in a data warehouse, like I mentioned before, we do not make updates. We store only new records. And even if there's a change that has been done in the operation system, that is also stored as a new record. And given this, if we were to normalize the data in a data warehouse as well, following these operations, then you'll see that the performance will be very, very slow. The joins are a very costly operation in a database. You must avoid it as much as possible. So hence, be familiar with the normalization, know what it means, so that you can avoid doing this in the data warehouse. So the question here could be misleading to some of you. What is the benefit of normalization? Yes, there are benefits, but those benefits are limited to the OLTP system, the transactional system, not the data warehouse. In data warehouse, we denormalize the data. Moving on. What is an ER diagram? So ER diagram is a entity relationship diagram. So ER stands for entity relationship, right? And it shows the relationship between the different entities within the business event. So take sales as an example, right? Your customer is an entity, product is an entity, store is an entity, and so on. Each of these entities will have functions such as a store can have an inventory, a store can have a promotion, right? A store will have an opening time, closing time, and so on. So entity relationship shows you how these entities exist, how they interact with one and the other, right? So for example, the customer entity can interact with the store entity, it can interact with the product entity, and so on. So when it comes to data warehousing, we usually don't follow the entity relationship diagram. Entity relationship diagram is again a purpose built for transactional systems, not data warehouses. For data warehouses, we use dimensional modeling. So dimensional modeling is a process by which you collect data for a specific subject area. You don't worry about the entities or relationships. Instead, your focus is on what is the business event that is being measured. So continuing on the same, what is a dimensional modeling? We've already discussed what are dimensions and facts, right? So the design approach that you take to design dimension and a fact table is called a dimensional modeling. And a dimensional modeling, you start by selecting a business grain or a business event, right? So for example, sales is a business event, shipping is a business event. You start with the event. Once you have identified the event, then you identify what is the grain of the event, and then you identify what are the dimensions that are in play in that event, and then you end up with your dimension and fact tables. So this is dimensional modeling in a nutshell. And what are the different phases of dimensional modeling? It's also called types. So when you're building a dimensional model, you usually start with a conceptual model, right? A conceptual model is a very abstract diagram that shows what are the different dimensions, what are the different facts. A conceptual model will not have too many details like what are the attributes, what are the primary key, foreign key, data types. None of these details will be there in the conceptual model. It's at a very abstract level. The reason it is kept so abstract is that changes can be easily made to it, right? So business users can validate very early in the design lifecycle if all the dimensions and facts are captured. Once this conceptual model is refined, you move over to the logical model. So the logical model will expand on the conceptual model by adding attributes, right? So we discussed, for example, customer dimension can have attributes such as first name, last name, middle name, age, date of birth, and so on, right? So you add attributes, you also add the primary key foreign key relationships, and you make sure that the attributes have a business friendly name, because the logical model again will need to go through the review of a business users. They need to validate if all the data that they need is available in the logical model. Once a logical model is refined, then you go ahead to a physical model. So physical modeling will convert your logical model to a set of tables and columns specific to a database. Another thing to note here is that when you build a logical model, it is not specific to a database. It can really be implemented in anything. It can be a database, it can be a OLAP cube, or it can be even a reporting tool. When it comes to the physical model, a physical model is specific to a database. So since a physical model has the data types, right, it has to be specific to, let's say, SQL Server or Oracle or Teradata, MySQL, or even SSAS cubes, right? So as you progressively move from a conceptual model to a logical model to a physical model, making changes to it get more and more difficult. So it's very difficult to make changes in a physical model, difficult in terms of the time it takes, whereas it's much easier to make changes to a conceptual model or a logical model. This is where tools like Erwin, Power Designer, they come into play. These data modeling tools help you convert automatically from a logical model to a physical model given a database. You simply need to select the target database type, and these tools will convert the logical model to a physical tables and columns based on some rules. Another thing to note here is that in the logical model, we refer the tables as entities and attributes, right? We refer to them as entities and attributes, but the same entities and attributes, when moved to the physical model, they are referred as tables and columns. This is something to be aware of. And the process of converting a logical model to a physical model is called forward engineering. Okay. Another important topic, slowly changing dimension, right? So the SCD stands for slowly changing dimension. Now, think of an example of a product, right? Assume that the product is being sold, right? And you have an existing data warehouse for it, right? So product will be stored in a product dimension and all the sales are being captured in a fact table. Now, after some time, you decide to change the name of a product, right? Based on customer feedback. So you do some survey and you find that customers find the product name not so fancy, right? They don't find it attractive, or there's something about the name that's keeping them away from buying it, right? So you decide to change the name of the product. So when you change the name of the product, you are doing that in the transactional system, right? You have a product inventory where you go ahead and update the name. While you update the name, the ID itself, the unique number attached to the product, that won't change. That still remains the same. Once you make this change, this data will flow into the data warehouse as well. So in the product dimension, you need to capture this change. How do you do that? You usually do that by inserting a new record with the same product ID, but the new product name, and also recording the time at which the record came in. So how is this helpful? When you join the dimension table, the product dimension table with the sales fact table, you can see how were the sales before the change in the name and how are the sales after the change in the name. So the ability to store history in the dimensions lets you do analysis and check the performance, right? Do the business measurement before and after an event, right? So this is an example of why we need to capture any changes in the dimension, and it is achieved through this technique called slowly changing dimension. Now, slowly changing dimension again are several types. We have SCD 1, 2, and 3. In SCD 1, if there is a change in the source system, we simply insert or we simply overwrite the value in the data warehouse. So in the example that I gave, if the product name were to change, we will not keep the historical name in our table. We simply overwrite that same record with the new product name. So depending on the requirement, if the business says that we really don't need to keep the history, we can take this approach of SCD1. SCD2 is where you insert a new record, but you keep a timestamp on when the new record came in. Then SCD3. So SCD3 is where instead of adding new records, you add a new column and you move the historical data over there. So you have something like old product name and new product name as two columns in the product dimension table. And of these, there is another type as well, which is SCD type 0. That's something that may come up. So in SCD type 0, there is no action taken, meaning even if there's a change in the transactional system, we really don't update the data in the data warehouse. So that is SCD type 0. For even a detailed explanation, please look at the Wikipedia page for slowly changing dimension. There are plenty of examples that can be easily understood. Okay, Pawan has a question. Do we set up SCD at the dimension level? Okay, that's a very good question. So Pawan's question is, do we define every dimension table as one of these types? Well, you can do that depending on the business requirement. However, the tools these days, the ETL tools, support handling SCD differently for different columns within the same dimension. So to give you an example, let's assume there is a data warehouse for a school, right? And the data warehouse is collecting data from admissions, right? Grades and so on. So you can use any ETL tool like Informatica or Talend, and you will apply a SCD rule. And this SCD rule can be specific to each column. So for example, it's quite frequent that students, when they're enrolling for the very first time, there is some typo in the names, right? So the first name or the last name may be slightly off, or the initials may be slightly off. In that case, you can set the first name and the last name of the student dimension as a SCD1, which is the moment there is a change in the transactional system, you overwrite the data in the data warehouse, right? There can be other changes such as the contact details or the address. That is something you would want to keep it as SCD2. So you can track that, earlier the students were at this location, now the student has moved to a different location, right? So you can set the address field to be SCD2, right? SCD3, you can store it for, let's say, the contact details, right? What was the previous phone number and what's the new phone number, right? Or what was the previous house the student belonged to and what is the new house, right? So that's something you can do. And let's say gender. Gender is something that you can set as SCD type 0. So if the source system changes the value for the gender for a student, you probably know it's happened because of a mistake, and you don't want to reflect that in the data warehouse. So for such attributes, you can set it as SCD type 0. All right, moving on. What are the key columns in fact and dimension tables, right? So the term key column refers to any column or a set of columns that uniquely identify the records, right? Or in the context of a data warehouse, it's primary key or foreign key. So if you look at this example here, we have a department dimension in which department ID is the primary key, right? And department name is just the description. And we have an employee table, right? Where we have the ID is the primary key, and then we have department ID as a foreign key relationship, right? So these are considered key attributes, right? So any primary key, foreign key are considered key attributes. They help you join these two tables. So similarly, a dimension and a fact table will have foreign key relationship to primary keys in the dimension table. Okay. The other question is, what are the different schemas that are implemented in a data warehouse, right? So I'm sure all of you are aware of star schema, a snowflake, and a fact constellation. So for some of you, the words snowflake and fact constellation may be quite overwhelming and quite new, but let me tell you, it's not very different from a star schema. It's all about the number of tables that you're looking at or you're analyzing at any given time, right? So let's start with star schema and explain what it is. So a star schema is a diagram, right? I repeat, star schema is a visual representation of the tables for a specific subject area, right? So for example here, this is a star schema for sales, right? At the heart of this diagram is the fact table surrounded by one level of dimension tables. I'm using the word one level because there is no other dimension table that require more than one hop to the fact table. Or in other words, all the dimension tables can connect to the fact table with just a single join, right? So this kind of a setup is called a star schema. So one misconception is that the databases should be a star schema. The moment you add another table to it, it's not a star schema and so on. The truth is that star schema is something that you share with the business users so they can understand the business model easily. So for example, if somebody were to ask you from the business side on what are the tables that I need from the data warehouse to measure the sales activity, right? So in response to it, you would share a diagram with them with these 5 tables. So for someone who looks at it, it's easily understood that, okay, there is a dealer dimension, a branch, a product, and a date, all connected to the sales fact table, right? So this is an example of a star schema. Snowflake schema expands on a star schema. So you see here, we still have the 5 original tables as per the previous slide. We have 3 additional tables, right? So how do you identify a snowflake? If you have dimensions that require more than one join or that join to one dimension table and then to a fact table, then this diagram is called a snowflake schema. We call it a snowflake because it is having multiple branches away from the fact table, right? And for a business user, this is quite a lot of information to process, right? So they need to understand how to join these 2 dimension tables to arrive at a fact table. They need to make sure they use the correct join conditions. Also, the performance will be a little slow because we have more joins now in a Snowflake schema. Again, Snowflake is a visual representation. There could be many more tables in the database, but when in response to a business user saying, give me all the tables for sales event, you would share a diagram that looks something like this. And you would add the additional tables as well because all these tables are related to the sales event. Moving on is a galaxy schema, or also called as a fact constellation schema. Right? In most projects, this is how the tables are going to be. Right? You have fact tables for multiple business events. So here you have a fact table for products and their variants, and here you have a table for sales. You see how the dimensions are being shared, right? The product dimension is associated with this fact table. The branch and date are associated with both the fact tables and so on. The dimensions that are at the center of this diagram, the branch and the date, are examples of conform dimensions. So probably we started by building a data warehouse for the sales, right? And then we eventually added a fact table for the product and their variants as well, right? So this is an example of a galaxy schema. In most cases, all your data warehouse will look something like this, right? But it's up to you on how do you categorize them, right? So when the user says, which table should I access for looking at the sales, then you must share a diagram like this or the list of tables like this. Or if the business user asks, how do I do analysis across sales and product variants? In which case you will share a diagram that looks like this, right? So as you see, star schema, snowflake, and fact constellation are not very different. It is just how you represent the tables to the end users. How do you present it to them? In reality, all the tables may be stored in the same database. Moving on. The next question is, what is real-time data warehousing, right? So real-time, as the name suggests, real-time is the capability by which you view something as it happens. So an example is a bank transaction, right? When you make a bank transaction, you see that on your statement immediately. When I say statement, the list of transactions. So let's say you withdraw some money, right, from the ATM, you get a message on your mobile. And at the same time, if you were to log in to your net banking application, you will see the transaction showing up there. That is real time, right? Something that happens immediately. So how does it apply to a data warehousing, right? So far, we have learned that data warehousing is the process by which you collect data from source systems, all right? And the data flows into the data warehouse. Most cases, there is some latency with which the data moves, right? But in some extreme cases, they want to look at the data as it happens, right? So it can be enabled. However, it demands a completely different architecture, right? You need to look at your source system almost every second, every minute. The moment a transaction is created, you quickly move the data to the data warehouse. So although it takes a separate set of architectures and very demanding, it can be achieved. And using the word real time could be slightly problematic. Instead, we could use the word near real time. Okay, because the process of moving the data right from the source, transforming it into a dimension and fact, loading it, and that appearing in a report will usually at least take a couple of minutes. Hence, it's also okay to use the word near real time data warehousing. And this is where we use some advanced tools such as data streaming tools, Apache Kafka, and there are other frameworks that support reading data as it happens through database logs and transferring them to a data warehouse or even a big data platform such as Hadoop. Finally, the other question that's asked is, which language is used for defining a schema in a OLAP or data mining? So for data mining, we use something called as a data mining query language, right? So this is a language that is used for defining schema on which the data mining algorithms run, right? So this is very different from your SQL, and it's also different from MDX queries, which you write on OLAP. So this brings us to the end of the questions that we had. Are there any questions from anyone? Okay, Bharat has a question. What is big data and how is it related to the data warehouse? All right, that's a good question. So big data is not to be mistaken as a replacement for data warehouse. Big data is an infrastructure, and the most popular name in big data is Hadoop and its ecosystem. So within Hadoop, you have HDFS, you have Hive, you have Impala, and so many other tools. Big data is a framework that supports storing vast amount of data with inbuilt data redundancy as well as parallel processing, right? So it complements a data warehouse, but it's not a replacement for data warehouse. You still need dimensional modeling. You still need to transform the data. However, the amount of data that is stored, the speed with which you can access the data is significantly improved in a big data system. All right. So if no more questions, then I would like to wrap up this session. Thanks everyone for joining this call. I hope you found it useful and you can apply some of this knowledge for your job interviews. Remember, please head out to the Edureka website. There are plenty of courses available for data warehousing, and there are plenty of courses that are specific to tools such as Tableau and Talend as well. And there is a very active support group and a very active forum as well where you can post your questions and get answers from experts. So with that being said, I would like to wrap up the session. Thank you so much and wish you all the best.
I hope you enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply to them at the earliest. Do look out for more videos in our playlist and subscribe to our Edureka channel to learn more. Happy learning!